A first-order differential equation is called separable if it can be put in the form seen here. The defining characteristic is that when you isolate the dy dx, it can be expressed as a function of one of the variables x multiplied by a function of only the other variable y. And separable equations provide the ideal starting point for solving first-order equations because the solution method is extremely intuitive. We simply do as the name suggests. We separate out. So I'm going to think of the dy dx on the left as being two separate entities, dy over dx. And with that in mind, we will separate out these variables. Let's bring all of the y's to the left and all of the x's to the right. So dividing both sides by h of y and multiplying both sides by dx gives us the following. And I think immediately upon inspection, it almost jumps out to us that it looks as though we are missing something. And to find our solution, we simply integrate. Once you've antidifferentiated both sides, you would have an implicit solution to the differential equation. If you can solve for y, you could get an explicit solution. So let's look at a simple example to demonstrate this process. The differential equation we're given is first order, dependent variable x, independent variable t. And on the right-hand side, note that this really does separate out. You have a function of x, so this could be playing the role of g of x above, multiplied by a function of t, call this h of t. First order separable differential equation. Because of having the dx dt on the left, we'll want to leave the dx and group t's on the right. So I'm going to divide both sides by x squared plus 1. And then multiply both sides by dt. And now that we've separated, we need to antidifferentiate. So in this case, the antiderivative on the left, I think, is maybe the quicker, more efficient one because it's simply a common formula. So this would be arctangent of x. And note, we do need to include a single, plus c somewhere. We could put it on the left or put it on the right. I'm going to go ahead and put it on the right when we take care of that integral. In terms of antidifferentiating the natural log, this is one of those kind of ideal scenarios for integration by parts. And when we use integration by parts, we need to make a choice between what is playing the role of u and what is playing the role of dv. But remember, whatever we let dv be equal to, we need to antidifferentiate it to find v. So in our case, the natural log t naturally can only go in that choice for u. So u would be natural log t, dv would be dt. And in this case, that leaves us with du being 1 over t, and v, the antiderivative of dt, is simply t. Integration by parts tells us the integral of u dv, which we have, is uv minus the integral of v du. So that would be t natural log t minus the integral of t times 1 over t. And I'm going to go ahead at this point, just so I don't forget later on, and immediately put that plus c on the right. And note what remains is a quick, efficient integral. T times 1 over t would simply just be 1, which leads to the following. And note, at each step in the process, we rewrite each side. Using good notation, things like equal signs, differentials, and we go until we've finished evaluating, in this case, all of the integrals. And finally, we are left with an arctangent of x on the left, and on the right we have t natural log t minus t plus c. And at this point we've been asked simply to solve the differential equation, so we could actually stop. This is a perfectly good implicit solution to the differential equation. But at the same time, if we wanted to, we could take it a step further and solve for x explicitly as a function of t. So in this case, x as a function of t is going to be the tangent of everything that's on the right. And with that, let me just note that we can clearly see every separable differential equation requires us to evaluate two integrals. So it's extremely important for us to be quick and efficient using our standard formulas and techniques of integration. Many resources can be found in Canvas.